Good morning, good afternoon, good evening. Whatever the case may be, we are back and better than ever. And we are continuing our study of calculus and the optimization. And certainly, every breath you take, every move you make, and every smile you fake should be dedicated to the learning, living, and breathing of the calculus. Let us continue our quest. We have a 4-liter container, and it must have a square base, vertical sides, and an open top, as pictured here. Find the most economical shape which minimizes the surface area of material. So I'm underlining a couple of important things here because we have no function here, and when we don't have a function, we need to make a function of what it is that we need to maximize or minimize. So we need something for surface area, and we know something about volume. I'm going to start with the volume. This is a rectangular prism. It has a square base, so each of these sides we will call x. We're not sure what the height is, so I'm going to call it y. And if that's the case, the volume of that container is going to be length times width times height, which would be x squared y. Now, we know the capacity is 4 liters, and what we also know is that 1 cubic centimeter, we know that 1 liter is equal to 1,000 cubic centimeters. And if you didn't know that, you know that now, and you should know it. So that means the volume, if there's 4 of them, is equal to 4,000 cubic centimeters is equal to x squared y. So we have one formula. Okay. Well, what about the surface area? Okay. The surface area is going to be the area of the base. Let's see, the area of the base times, or not times, plus the area of the 4 sides. And each side has an area of x times y. So the surface area is going to be equal to x squared, the area of the base, plus the area of the 4 sides, each of which are xy. So that's 4xy. And we need to minimize the materials we use. We want to minimize the surface area to make it the most economical because, of course, that would cost less. But our problem is we have 2 variables. Okay? But what we do know is this relationship right here. So I can easily solve for y and have 4,000 over x squared is equal to y because these are the same x's and y's, and then we just simply use substitution. So area would equal x squared plus 4x multiplied by 4,000 over x squared. Okay, and if I clean that up, I finally get area equal to x squared plus 16,000 x to the negative 1. And I want to maximize that, so to find the maximum, I need to take the derivative. So the derivative would be 2x minus 16,000 x to the negative 2, or 2x minus 16,000 over x squared. So to find the minimum, I need to set this equal to 0. So the derivative equal to 0. So I would take 2x minus 16,000 over x squared, set it equal to 0. I'm going to multiply everything by x squared to clear this fraction, and that would give me 2x cubed minus 16,000. X squared times 2x is 2x cubed, x squared times 16,000 over x squared is a 16,000, and x squared times 0 is 0. So solving this, 2x cubed would equal 16,000. X cubed would equal, oh, I'm so popular. Stop it, stop it. Okay, x cubed would equal 8,000. So then x would equal the cube root of 8,000. Okay, and 8's looking good. I know 8's a perfect cube. So that should give me a little hint or let me know, oh, that means the cube root of 8,000 must be 20, or 20 times 20 times 20 is equal to 8,000. So now I'm going to move, I ran out of room, so I'm going to move over here or up here and do my sign diagram test. So 20, yes. And I'll use a test point in the derivative for something less than 20, maybe 10. So if I replace x with 10 here, I would get 20 minus 16,000 over 100. Clearly that's going to be negative, yes. And then if I choose something greater than 10, greater than 20, let's say 30, so that would be 60 minus 16,000. 30 times 30 is 900. Okay. Well, all I need to know, is this going to be positive or negative? Okay. Well, let's think about 900 and 16,000. So 900, it's not going to take a lot of 900s to get to 16,000. So this is 60 minus it is certainly going to be positive. So I get positive here, which confirms that 20 is indeed a minimum. Yes, nice. So we have found our value of x, and x represented the base or the sides of the base of this container. So that means x equals 20, which means that y is equal to, let's see, here's an equation for y. Do we have anything better? Not really. So 4,000 over 20 squared is 4,000 over 400. Is that what that's going to be? It is, and that is equal to 10. Okay, so find the most economical shape. So that would mean we would need a container with a base of 20 centimeters by 20 centimeters. Oops, by 10 centimeters. And there we go. We have done it. Let's see if we can take a look at that on the calculator. Let's see, let's remember this. X squared plus 16,000 x to the negative 1 is our surface area. So, oops, wrong one. Let's do a new, add a graph. Okay, so that's going to be 16,000 for my surface area. X to the negative 1, I did this a little backwards, and that is plus x squared. And let's just take a look at that graph. And we think the minimum occurs at 20. And of course, we're not going to be able to see it, so let's just take this out to, we know it's our x is 20, so maybe we go out to 30, and it's not high enough. But let's think about this. I don't know, let's go up to maybe 20,000. See if we can see the curve. We had a 16,000 involved, yes. And let's see if we can find a minimum. Menu, analyze graph, minimum, to the left, to the right, and we got one at x equals 20. Doesn't look that good because we have a bit of a big graph. I am going to maybe zoom in and see if we can see it a little bit better. A zoom box right there. Maybe it'll look even better as a minimum. I'm not sure how it's going to look. Oh, it keeps flattening out. But we know it's a minimum. We showed it with the calculus, and the calculator verified that. All right, that is it. I am out. Looking forward to part 3.